Yes, first your questions. Your question. Okay, I can translate.
Hocam, şimdi query report yazarken probability density function kafa yorayım dedim tam ne olduğunu anlamak için. Benim anladığım kadarıyla mesela bir seçim yapılacak, atıyorum 1 ile 2 arasındaki integer'lardan bir seçim yapılacağımız zaman 0 ve 1 şansımız var. Dolayısıyla seçme imkanımız herhangi bir piyasa olmadığı sürece 1/2. Ama mesela 0 ile 1 arasındaki bütün reel sayılardan seçim yapacaksak 0.5 seçme probability'miz 0. Bunun için hani probability'yi kullanmak yerine probability density function kullanıyoruz. Bu mesela 0.5'e ne kadar yakın bir sayı seçebileceğimizi ifade ediyor. Yani bu interval, belli interval için infinite seçenek olduğunda bunu veya continuous bir şey olduğunda bunu kullanıyoruz değil mi?
So let me just paraphrase the question. What is the relation of probability density with probability? Okay. Your friend has pointed out, for example, if you are just throwing dice, there are 6 outcomes which are discrete. And if the dice is a fair dice, then the probability of each one of the outcomes is 1/6. They should be all equal. Then the question is, let's say, what about the probability density for the position of an object? That we will be talking about. We will be talking about electrons. Well, the electrons can be anywhere. They don't have the position of the electron will not be discrete. In that case, we cannot really talk about, if you ask me what is the probability that the electron, which is moving in one dimension, what is the probability that the electron will be at that point? What can you say? I know it's the probability of observing the electron at that point. And you should also know. Let's forget about the electron. Let's look at his example of choosing a real number between 0 and 1. What is the probability of choosing, let's say, 0.5? Which is 0. The probability of choosing just one number out of infinitely many numbers, if the probability is uniform, or even if it's not uniform, will be 0. Here, the probability of observing the electron precisely at that point will be 0. The probability of observing the electron in a very small region near that value might not be 0. So because, as your friend pointed out, since we have a continuous values, we have infinitely many outcomes. And if you ask what is the probability of one outcome out of infinitely many of them, the probability will always be 0. So, but that's not what we actually do in experiments. We can never measure precisely the position of anything, because all the physical experimental apparatuses, they will have error bars. Plus, now we know that due to quantum mechanics, the nature itself has some uncertainty. So there will always be some error bars. What we can only do is ask the question, what is the probability of having, let's say, I have an electron in my system, somewhere over here, in this range. I can ask the question, suppose I try to see whether the electron is in this range, because my devices can only measure certain ranges. What is the probability that if I look whether the electron is in that range or not, what is the probability that I will see the electron there? That's the probability. Then that we will write in terms of probability density. Now, in this case, the probability will not only depend on the x position, but it will also depend on the width of that segment. Not only at the position, but also on the length of that segment. So if you say that the probability of observing the electron, let's say it's x and dx. Now I have two parameters. I have to specify two parameters. One, the position, and the second one is the thickness of that range I'm looking for. Well, usually what we do is we just set this thickness to 0. But we already know that if dx goes to 0, the probability should be exactly 0. So you can say that essentially we are making a Taylor expansion. This will be px dx. This is the probability. This is my probability density. Probability, what is the unit of probability? It doesn't have any unit. What is the density of probability density in one dimension? Probability per meter. Probability per length. So it's 1 over meter. Now I can also ask, what is the probability that you will be in the classroom, you are in the classroom now? You are a macroscopic object. And I will say that the probability that you are inside the classroom is 1. Well, let's just continue. Now what quantum mechanics tells us is that this probability density can be written in terms of something else. So-called the probability amplitude. Now we had already seen one probability amplitude, one case of a probability amplitude when we were looking at particle in a box. When we had this particle in a box of length L, we had said that the wave function should have such a form, where this kn should be an integer multiple of pi over L. So let me draw a couple of probability. Let me first draw a couple of wave functions. It can have this shape. This is the ground state. If you look at the excited state, first excited state, it will have this shape. These are the psi. Now I can talk about I can also draw the probability densities. Well, this will more or less have the same shape. The second one will have such a shape. You see, in the first excited state, the probability density at the center of my well of the box is 0. So we had already imposed the boundary condition that at the edges it should be 0. But now in the first excited state, I have a large probability of observing the electron in the left half and a large probability of observing it on the middle of the right half, but there is a negligible probability of observing the electron in this region, close to the center. The probability density right at the center is 0. But since when we are making an actual measurement, it will always be a range. And if you choose a very narrow range at the center, the probability of observing the electron in that range will be negligible. Of course, these probability densities, by the way, they can also depend on time. They can evolve if the system has some dynamics. The average of what? Well, let's call this psi 1. Let's call this psi 2. Let's call this psi n. If you call the average this one, This is 1. Because definitely we are already told that there is a particle inside. We don't know its energy, we don't know where it is, but there is definitely a particle there. So the probability of observing a particle somewhere within this range, which is given by this integral, should be 1. Other questions? Well, let's see. Well, okay, nice question, because it will be also related with the correspondence principle. You see, if you would look at this problem from a classical perspective, what is let's say we choose a range. Let's call this delta x. And let's say we have a classical particle just bouncing back and forth with some velocity v, with some speed v. What is the probability that I just choose a random time? What is the probability that I will observe this classical particle at this point? In this range, not at that point, but in that range. Well, I would rather go with time. You see, in this classical problem at least, the randomness is I just choose a random time. So there are many time points that I could have chosen. And now we can add, in some of those time points, it's in this interval. In the others, it's not in that interval. So I just need to take the ratio of those two. How long does it spend in this interval? Let's say as it starts from here, goes there, and comes back. How long does my particle spend in this interval? Delta x over v times 2. Because it spends delta x over v on its way here, and then another delta x over v on the way back. How long does this total trip take? L over v. So this is delta x over L. So the probability density is just 1 over L. It's just constant. So classical physics tells me that the probability of observing the particle at one point or the other point should be equal. But that is not what quantum mechanics told us, at least in the ground state and the first excited state. In the ground state, it said that the probability of observing my particle close to the edges was 0. In the first excited state, the probability of observing my particle at the edges and also at this point is almost 0. But now let's come to your question. What happens when the n is huge? We have many oscillations within this length L. Let me try to sketch that. Let's say n is huge. So it will just oscillate wildly. So let me just draw it from here. So this is what I will see, more or less. Now let's come to the measuring device. You see, when we make a measurement, I will never be able to determine the probability of observing the particle exactly at that point or at this point. I will always have a range. And if n is huge, that means within that range, although it might be very small, but within that range, there will be many, many oscillations. So I will just see the average. So you see, the probability density is a times sine kn of x, all of these things squared, or a squared times sine squared kn of x. This is the probability density. But if the sine is oscillating wildly, what I can determine is only its average, which will be just 1 over 2. Which is constant. So this is my psi. The probability density that I can actually measure will be just this one. It is flat and constant. In fact, this a squared is nothing but 2 over L. So they agree. Well, I didn't calculate it, but if you calculate it, it's just 2 over L. So in the large N, what I will measure, what I will observe, quantum mechanics predicts that what I will observe for huge N is nothing but the classical probability density. Well, you see, what we are saying over here, see, this is the wave function of an electron. Where is this electron? It doesn't have a position. I'm not saying that the electron is here or there. It doesn't have a position. Classical physics says that it has a position. We might not know the position, but it's definitely somewhere with a position. What quantum physics tells us is that before you make the measurement of the position, it doesn't have a position. Only when you make the measurement, it acquires a position. So if you would compare Newtonian physics and quantum physics, in Newtonian physics, the position of an object is an inherent property of the object. The object has a position, whether you know it or not. But quantum physics tells us that, no, it doesn't have a position until you measure it.
Bunun sebebi de şey mi? Çift eğri filminde ölçtükleri zaman kaçlık olarak davranıyor, ölçtükleri zaman dalga olarak davranıyor.
Well, you say, why does it behave like that? What is the reason? We don't know. We just can describe it, but we don't really know why. Why does the nature exist? We don't know.
Yani şey nereden geliyor hocam? Konu yoktur.
Let's say that is one of the interpretations, so-called the Copenhagen interpretation. Well, there is a different interpretation which loses its supporters, let's say, quite fast, so-called the hidden variables. No. What hidden variables tells us that, well, we are saying that we don't know the position. There is this uncertainty principle. If you create identical systems, every measurement will give a different result. Some people, at least in the beginning, were saying that, okay, maybe position and momentum are not the variables that we should use to describe nature. And they say that maybe there are some other variables which we are unaware now, and we are not able to control. And maybe if we could control those variables, we could have predicted the outcome of the measurement. So they were, in a sense, saying that the electron had a position which is determined by these hidden variables. But the new experiment, especially some recent experiments, says that no, it cannot be. There cannot be hidden variables. So it seems that the nature just behaves like that. We don't know, the outcome doesn't exist before we make the measurement. Falsifies. Well, you see, the hidden variable is like this. Let's say you have many gloves, okay? Many pairs of gloves. And somebody just puts one of the pairs in one box and the other pair in the other box. Randomly. You don't know which one is which. But there is one thing you know. If there is a left hand in one of the boxes, there's a right hand in the other box. So kind of this is a hidden variable, and you can think of this as a hidden variable theory. In the box, there's either the left hand or the right hand, one of them. But it's either the left or the right. You might not know it, but it exists. And if you just make measurements of both of the boxes, you will say that, oh, they are correlated. So if there's a left hand over there, there will be a right hand over there, etc. Now, what is tested is we created such pairs, not of gloves, but we created such pairs of, I think it was the photons. And so if you make this assumption, well, I just advise you to read called the Bell inequalities. You see, these Bell inequalities, if I'm not wrong, they practically depend on this fact. A dot b squared is always less than or equal to a squared times b squared. It's such an equality. And but in these equalities, most of the time, what they measure is not the position, but the spin. And well, it's just the rotation of itself, the angular momentum of these particles. So if the spin is determined before the measurement, there's an inequality you have to satisfy. If that inequality is not satisfied, then the spin doesn't exist beforehand, and that's what the experiment they do. Now, spin, we will not discuss it yet until the end of the semester. Hopefully, in the last weeks, we will discuss the spin.
Eğer hidden variable'lar varsa, ölçmem gereken şeyi nasıl tahmin edebiliyor şey olarak bir ekran var. Bir şeyleri ölçüp bunlar yok diye bilmek için önce onları ölçebilmem veya ölçememem gerekiyor.
No, you see, what hidden variables tells you is that the outcome of the measurement is already determined beforehand. That's what the idea of the hidden variable theory. And that outcome is determined beforehand by these hidden variables. What this Bell inequality tests is whether the outcome is determined beforehand or not.
Outcome nedir bu?
The direction of the spin. So the direction of some kind of an angular momentum of these particles. If that angular momentum exists beforehand, there's an inequality that you have to satisfy. If it doesn't exist beforehand, you don't need to satisfy that inequality. I mean, it's not really a technical paper. I mean, I do suggest you to read it.
Are those hidden variables and this probability theory only possible explanations, or are they just, for example, propose another theory that explains the inherited, maybe, evolution?
What do you mean? Well, inherited basically means you are defining this hidden variable as your inheritance. So this argument basically just Well, there's still one loophole left. And that loophole just basically tells us that the measurements that we are going to do is already determined beforehand at the beginning of the Big Bang. Well, I mean, if you believe, I mean, you either choose that at least the spin isn't determined before the measurement, or you choose that there is no free will.
Does this have something to do with Stern-Gerlach experiment?
Well, the experiment is quite similar to a Stern-Gerlach experiment. But at least, I mean, when I'm teaching the first-year students, I always tell them not to trust me. They should convince themselves. But here I will say that, trust me, the position doesn't exist before measurement, at least according to the Copenhagen interpretation. Now, I do suggest you to read something about these Bell's inequalities, about Copenhagen interpretation. Let me write these first. Decoherence and multiverse, many worlds. They will make nice reading for the summer. Yes? Well, you see, no. You see, if you look at this electron, or this particle, let's say, in this particle in a box, well, you can say two things. Either its position doesn't exist, or it is everywhere at the same time. But also don't confuse it with the fact that your friend was pointing out there's a sentence in your book. The position is spread out, but the electron is not. Meaning that if you say that the electron is everywhere, what will be the outcome if you just put a wall over here suddenly? Put a wall over here. So will you get half an electron? No, that never happens. When you put a wall over here, there is a 50% probability that the electron will be over here, 50% probability that the electron will be over here. But in any case, if you get an electron in one of the halves, it will be a full electron. And you have no idea which one is, where the electron is, before actually going there and measuring it. Well, let's see. You can have, is this what you are asking? Well, let's say I have an electron. I get a box, put an electron in between, and then shrink my box. What do I get? Well, I get an electron who is a wave function looks something like this. 0 outside, very large in this range. I can what happens if I shrink it further? Well, this wave function becomes even narrower. But then keep in mind, by shrinking the box, you are reducing the uncertainty in the position. If you reduce the uncertainty in the position, there will be an increased uncertainty in its momentum or its kinetic energy, which means the pressure will increase. And in fact, for example, white dwarfs are basically stable. Well, they're one, the uncertainty principle, and the Fermi exclusion principle, which stabilizes it. Even if there is no heat, you cannot just squeeze them further. For example, the electron cannot be found in the nucleus, but it can still be found in the atom. Because if you would shrink the electron, compress the electron to a volume the size of the nucleus, its energy should be of the order of mega electron volts. Whereas the electrons we measure have energies of the order of electron volts, not mega electron volts.
And we are measuring from photoelectric.
We are measuring from photoelectric effect, ionization processes, or now there are the other kind of electrons like the beta decays. Those electrons have 1 or 2 MeV. Even that is not large enough, because if you put it in the nuclear, the energy should be tens of MeV, not 1 or 2 MeV.
Shouldn't the potential be lower as electron comes closer to the nucleus?
So the potential energy gets smaller, but the kinetic energy increases. That's what will create the pressure. You see, the ground state of the electron is kind of a balance between the potential energy and the kinetic energy. If you try to, the potential energy tries to attract it further, but then the kinetic energy increases too much. In fact, that is why the electron cannot fall into the nucleus.
The average energy decreases when the uncertainty of the energy are increasing. I couldn't understand how the average energy decreases when the uncertainty about.
Well, you see, this is what I mean. We looked at the problem of the hydrogen atom. No, the harmonic oscillator. P squared over 2m plus 1 over 2 omega squared x squared. This was one of the problems we had studied. And now what we said, well, let's say the P is of the order of the uncertainty, x is of the order of the uncertainty. So P would be typically h bar over x, h bar over 2x. Or delta P would be h bar over 2 delta x. So the energy of the system would be 1 over 2m h bar over twice delta x squared plus 1 over 2m omega squared delta x squared. Well, if you try to compress it, then this increases also. This becomes smaller, but this becomes much larger. So this function has a minimum. You cannot lower the energy below that minimum value. Basically, the same thing happens in the hydrogen atom also. If you try to compress the electron into smaller and smaller volumes, so delta X becomes smaller and smaller, kinetic energy increases enormously. Other questions? You see, we will be talking about, okay, the probability. Probability of what? Well, we will be talking about the probability of observing a particle in a small volume, delta V, around R. Let's just use the three-dimensional notation. So the probability of observing a particle in a small volume delta V, this is my R point. I imagine a very small volume around it. Then I can ask the probability of observing the particle within that very small volume. Well, that very small volume can take any value. It doesn't take discrete values. Similarly, R just can take any value, not necessarily discrete values. So what I can define is that this probability, as delta V goes to 0, I can call this probability as P of R times delta V. Well, the probability of having an electron exactly at this point will be always 0, because R takes continuous values. So this is what I call probability density. Now, I repeat, I define a density because R changes continuously. For example, why do I press on that? We discussed this particle in a box. In the case of the particle in a box, we studied the possible energy values. Now, the energy takes discrete values. In that case, I cannot define the probability density. I have to talk about the probability, because then I can ask you the question, what is the probability that this particle in this box is in the first excited state? That is a probability. I don't define a density there, because energy doesn't change continuously. Or if I can also do the same thing in the hydrogen atom. I can ask you the probability of observing an electron to observe in the, I don't know, the third excited state, or the probability of observing the electron in the ground state. These are all probabilities. There is no corresponding probability density because its argument takes discrete values, not continuous values. But here I'm talking about position, and position changes continuously. So I talk about the density, probability density. And what is this probability density? Well, in terms of this wave function, probability density is nothing but my wave function at the point R squared. So that is my probability density. There was one question over there. No, not you. You had some question? No? No, sen değildi. Okay, if you have a question.
Elektronlardan oluşan daha büyük makroskopik canlılar için ya da işte cisimler için aynı şeyi söyleyemiyoruz sanırım ama dediğini anlamadım. Mesela şey diyebilir miyim? Gidip görene kadar arabamın garajda durmadığını söyleyebilir miyim?
Well, even if you don't see your car, there will be some birds seeing your car, there will be ants seeing your car. Something is seeing that your car is over there. Well, the question where, you see, when we say that the measurement is still a problem that we don't understand. So we are here I was saying that the position of this particle doesn't exist until I measure it. Why am I special? What is so special about me? Or whoever is measuring? We don't know. We say that, okay, we are intelligent, we have the intelligence, so that makes the difference. Nobody really believes that. What is the measurement? As I said, there are many atoms over here. The electron is orbiting the nucleus. The nucleus is measuring the position of the electron, in a sense. The electron is measuring the position of the nucleus, but we are still talking about the probabilities. How do we make this transition? We don't know. That's the question whose answer we don't know yet.
Bu kendinden mi ortaya çıkıyor? Emergent property mi?
We don't know. You see, for example, decoherence is kind of that. For example, there should be a probability that you are here, you are at home, you are on a bus, you are just playing outside. You should have a wave function. But we don't see that wave function. You are here, unfortunately, right?
Çünkü wave function kollaps oluyor.
Is it? Or since when you become such a macroscopic object, you are interacting with so many things at the same time. It's not that they collapse, but all your interactions with the environment, with all the things making the environment, they are kind of localizing your wave function at that spot. There's no collapse, nothing like that. But all the interaction with the environment is causing your wave function to be zero everywhere except then close to your C. So that you are here and I don't see you as a spread out wave function. Probably the same thing happens for your car. Well, that's, as I said, the coherence is one of the interpretations trying to address this issue. But there is no generally accepted answer.
Hocam az önce söylediğiniz mesela arabayı başkası measure ediyordu mesela buna şey sayılabilir.
Who is the other one? Why doesn't he or she have a wave function?
How do you define measurement?
Well, how is the measurement defined?
Yani garajın tepe lambası bile o zaman bir measurement sayılmaz mı? Sayılır yani.
Can we consider it as a measurement or not? These are still open questions.
Interaction varsa measurement olması gerekmez mi?
But interaction is always, all the time, exists all the time. You see, just imagine the electron orbiting the nucleus. There's always interaction with the nucleus. So there's, if that were true, there's always some kind of a measurement. But still, we talk about probabilities. And we say that, okay, the electron doesn't have a position until we measure it. Why are we special? Good question. We don't know. How do you define, how do you make that distinction? We don't know. Sure, there are always photon exchanges between the nucleus and the electron. But we don't call the nucleus as an observer. It doesn't cause the electron to have a position.
Relative to us.
What does it mean?
I were nucleus, I would.
Anyway, there are still many questions about how we should interpret these things. Now, what your textbook will be, what we will be discussing, what your textbooks this year, also next year will be discussing, will be mainly the Copenhagen interpretation. We know that that interpretation works. Well, is it the actual reality? We don't really know. When the problems arise when you go to particular, what each particle will do. If you ask questions, what an electron will do, the Copenhagen interpretation just gives you probabilities and nothing else. But of course, if you talk about what 1 million electrons will do, well, then it becomes definite. You see, if for example, one of your friends had mentioned about the Stern-Gerlach experiment, you take one electron, send it through an inhomogeneous magnetic field. We don't know what it will do. You just create the electrons identically. Let's say some of them will go up, some of them will go down. How many of them will go up? Half of them. Well, half an electron doesn't go up. But if you have 1 million electrons, around 500,000 goes up, 500,000 goes down. If you have 10 to the 10 electrons, half of that goes up, half of that goes down. The error bar becomes much smaller as we increase the numbers. But if you just send 1 electron, we have no idea which way it will go, unless we prepare it in a special way.
Günümüzde fiziksel araştırmalar çoğunlukla interpretation.
Well, I can ask you, what else is there? You see, at the end of the day, whatever you know is an interpretation of your brain. Anyway, if we go that direction, there is no coming back. So let's go with quantum mechanics. Yes. I don't know. We didn't discuss it yet. You see, what we know is that if I send 5 million electrons through a specially prepared non-uniform magnetic field, half of them go up, half of them go down. None of them go in between. So which tells me that there is something else which can only take 2 values. That is what we call spin. So let's come back to quantum mechanics. Now what I mean by quantum mechanics is, okay, up to now we had discussed the basic concepts. We discussed about the wave functions. We have been discussing about the probability densities. Now we had already mentioned some of the probabilities of this wave function. It should be continuous. We can choose this integral to be 1 and differentiable. Its derivative should exist. Well, you see, these are the requirements we impose on the wave functions, and our predictions seem to predict the nature quite well. But we never asked, at least until now, we never asked, okay, so how does this wave function change with time? Up to here, in a sense, we were doing the analog of kinematics. Now we are asking the question, what about the dynamics? How does a given system, if you create your system, if you have a system with electron, how does it change with time? That is what we will be asking. You see, if you remember Newtonian mechanics, there is the Newton's second law, which allows you to determine how the position of the object will change with time. So this will be now what we will be looking at is the analog in quantum mechanics. So let's start with the wave function. Now, quite often we said that, okay, the wave function is, we use the cosines or sines, cosine kx minus omega t, or sine kx minus omega t. But a different representation of these wave functions would be just the exponentials. These are just as good. Are you familiar with these? So these exponentials you can just write in terms of cosines and sines. And well, the nice thing about cosines and sines is that they are real functions. So that if you are talking about a wave, which is the displacement of something from another point, it should be a real number. So that's why we most of the time stick with the cosines and sines. But here the wave function itself, well, we are not observing the wave function anyway directly. What we are observing will be the wave function, absolute value of the wave function squared, which has to be real. So the wave function can be real or it can be complex. There is nothing that prevents a complex wave function. So we will stick with the more general complex representation. So this is our wave function. One possible, let's say, wave function.
What does the complex part correspond to?
What does the real part correspond to?
If you take the square of it, the real part comes out and it gives us information about probability.
No.
No?
You see, if I have a wave function, it will have a real part and an imaginary part. The psi squared is a squared plus b squared. It's not the real part. It's the real part squared plus the imaginary part. Now let's come back over here. Well, this has a definite k and a definite omega. So it has a definite momentum and a definite energy. What is the probability density? How does it change from point to point? What is the absolute square? One. Constant. So this describes a particle who is actually everywhere. It has a uniform probability density. The probability of observing that particle at this point is the same as the probability of observing it here, which is the same as the probability of observing that particle in the Andromeda galaxy. How many of you watched the Hitchhiker's Guide to the Galaxy or read the book? What was the name of the drive? Do you remember? The infinite probability drive. So the idea was, if you, well, this is an infinite probability, infinite spread probability density, in a sense. Well, since there is the uncertainty in its position is infinite, the uncertainty in the momentum can be zero. Well, in fact, since the uncertainty in momentum of this particle is zero, it has a definite momentum. And it has a definite energy.
Are those assumptions?
No, I'm just looking at this wave. I'm saying, sorry? Yeah, I'm just, yes. I'm just looking at the wave. I'm kind of going backwards. What I'm looking for is, I'm looking for an equation that would allow me to determine the possible wave functions and also tell me how that wave function changes with time. So that is what we did in Newton's second law. We already knew the equation. We applied it in various different cases and determined how a given system evolved with time. Now we don't have the equation. So in a sense, we are going backwards. We have a solution of the wave function. This is a wave. And we know that this wave can describe a particle of a given momentum, h bar k, and an energy equal to h bar omega. Then we can ask the question, what is the equation that this wave satisfies? Can we generalize it to not this particular kind of wave, but for every wave? That will be the steps that we will be taking. So what do we know about the energy and the momentum of the particle? Well, the energy, it doesn't change. It is everywhere. So there is no force, practically there is no force acting on it. Its momentum doesn't change. So there is no force. So for this particle, if it is non-relativistic, the energy should be just p squared over 2m. You see, the momentum is given by h bar k. It is independent of time. So there is no momentum change. So there is no force acting on this particle. So there is no potential. So the energy of this particle should be p squared over 2m if it is a non-relativistic particle. Of course, if it's a relativistic particle, you can just change this equation. But for the time being, let's stick with the non-relativistic case.
How did you just cancel out the uncertainty momentum?
I didn't. I know that that particle has a definite momentum. What about the momentum position uncertainty? Well, since I know the momentum definitely, the uncertainty in position should be infinite. But it's already over there. The probability density is uniform. The probability density is not localized in a finite position. So the uncertainty in its position is infinite. So no problem with the momentum position uncertainty. Okay, then this will not be the wave function. You see, putting walls is the same as putting a potential energy. Now I'm starting with a simple solution. Simple, sensible solution. Well, this will be a particle of a given momentum. And now try to find the corresponding equation. And then I will try to generalize that equation to systems which contains potential energy. And then ask the question, does this equation make sense in simple other cases like the particle in a box or the hydrogen atom? But first let's start with the simplest case, the free particle. That's the simplest system you can imagine even in classical physics. So what is the equation that describes this wave function? Well, let's see. Now what I will try to do, okay, we know the energy, we know the momentum, and the energy and momentum should satisfy this relation. Now let me take some derivatives of this psi. You see, if you consider Newton's second law, it's a differential equation. So in physics, we are always used to having differential equations. Well, let me take the derivative of psi with respect to x. So it will be I times k times e to power I kx minus omega t, or h bar over I times the derivative of psi with respect to x will be just p times psi. P being h bar k. Let me do it once more. H bar over I del over del x. H bar over I del over del x psi is just p squared psi. Why? Because if I act this one on this, I get a p psi. Then I act once more on this p psi. Well, p is just a constant. If I act this one on psi, it brings me a second factor of p. Well, let me take the derivative of psi with respect to t. This will be minus I omega e to power I kx minus omega t, or I times h bar del over del t of psi is equal to e times psi. Now let's see, for this solution at least, I times h bar del over del t of psi, which is e times psi, but e is nothing but p squared over 2m psi, which is 1 over 2m p squared psi is h bar over I del over del x squared of psi. So at least for this particular solution I started with, I h bar del over del t psi, this is equal to minus h bar squared over 2m del squared by del x squared psi. Now the nice thing about this last equation is that, okay, first of all, it tells me how this changes as a function of time. But it doesn't have any reference. You see, our initial wave function had a definite k and a definite omega. But this equation has no reference to that particular value of k and particular value of omega. And now we take one more huge step. Well, this was based on e psi is equal to p squared over 2m psi. Now, what happens if there is a potential? Well, this will be modified. And it will become E of psi should be equal to p squared over 2m psi plus v times psi. Now my equation is this one. I times h bar del psi by del t is equal to minus h bar squared over 2m del squared by del x squared psi plus v of x psi. This is what we call the time-dependent Schrödinger's equation. Okay, before you go for a break, let me also emphasize one more point. These arguments in the last few pages is not the derivation of the Schrödinger's equation. There is no derivation of the Schrödinger's equation. All those arguments are just plausibility arguments. What we have argued is that because of those arguments, such an equation might make sense. How do we know that it is the correct equation? Well, we have to make predictions using that equation and compare those predictions with the experimental outcomes. Only then we can say that this is the correct equation describing nature. Just like Newton's laws. There is no derivation of Newton's laws. Similarly, there is no derivation of a special theory of relativity. What we had done when we were discussing special theory of relativity was discussing how we should modify our equations so that they agree with the experimental outcomes. The same thing holds over here. How should we modify our equations so that the predictions of the equations is in agreement with the experimental outcomes? We had already discussed some experiments like the spectrum of the hydrogen atom. We already know the emission spectrum, the absorption spectrum. We should make predictions about that. We somehow know the particle in a box problem. There are many problems that are similar to particle in a box. We should make predictions about that. Now, there will be another weird phenomena that we will call tunneling. We make use of that. We make microscopes, very powerful microscopes, to look at the atoms using that tunneling phenomena. So there is a strong experimental basis for the tunneling phenomena. Do we predict it? Only then, once we compare the predictions of these equations with the experimental outcomes, only then we can say that this is probably the correct description of nature.
Is there a loophole in this equation?
What do you mean by loophole?
I mean, is it applicable to all quantum mechanics phenomena? Like, why do we have direct equations?
Well, let's see where
these equations instead.
Let's see, where did we start to obtain this equation? Where did we use what were our plausibility arguments? E is equal to p squared over 2m plus v. Now there's a problem. This is the non-relativistic equation. What is the relativistic analog of this? What does the potential energy mean when you have relativistic mechanics? That's in itself a problem. So let's ignore the potential energy for the time being. What is the relativistic generalization of this equation? Well, we have E squared is equal to m squared c to the 4 plus p squared c squared. If you start from here, use basically the same plausibility arguments, then what you end up having is this equation. This is what is called the Klein-Gordon equation. Well, then you ask the questions. You see, the first equation, the Schrödinger equation, is first order in time, whereas this is second order in time. Now, what does that mean? Schrödinger equation tells me that if I know the wave function now, then I can determine the wave function in the future. But Klein-Gordon equation tells me that if I know the wave function now and the time derivative of the wave function now, only in that case, if I know both of them, I can determine the wave function in the future. Which one is correct? Well, it turns out that both are correct. The time derivative just changes the wave function negligibly. For most practical cases, you can just ignore it, unless you are really moving at relativistic speeds. But then there was the Dirac who asked, Well, why do we have a second order equation in time? So the Schrödinger's equation works perfectly with as a first order equation in time. Can't we write a relativistic version of a relativistic Schrödinger's equation with only first order equations in time? Then he had his Dirac equation. And later on it turned out that, for example, Dirac equation describes particles with spin. So there has to be, we can only use it for particles with spin like not the particles with spin 1/2 like the electron. For Higgs boson, for example, we have to use this equation, the relativistic analog. Anyway, we will not discuss these equations. We will stick with the Schrödinger's equation. In the future years, if you are interested, you can learn the other ones. Okay, let's give a 10-minute break, and then we can continue.